Hi, in this video I will talk about the halohydrin formation reaction, which is a combination of two reactions, the halogenation reaction and the hydration reaction. In this reaction, we add to the alkene a halogen, which is X2, and also we add H2O. We can also add any other alcohol or a nucleophile, such as ROH, for example. This leads to the formation of what we call a vicinal halohydrin, and by vicinal we mean that the groups are added to two adjacent carbons. So this is what we mean by vicinal. And halohydrin, halo because we have a halogen group, and hydron because we have OH group. So this reaction adds a halogen and an OH group. If we used alcohol instead of water, then we are going to add RO group, as we will see in the examples. So X usually adds to the carbon with more hydrogens, and OH or OR adds to the carbon with less hydrogens. For example, in this reaction here, we are adding Br2 and H2O. This carbon here has two hydrogens. This one here has zero hydrogen. So based on what we just discussed, X will be added to the carbon with more hydrogens, so that's why Br will be added to this carbon here. And of course, you remove one hydrogen from this, so you are left with OH, and OH will be added to this carbon. So this is how we complete the reaction. Let's take another example. Again, in this example here, this one has two hydrogen, this carbon has one hydrogen. Based on the rule that we just discussed, Cl will be added to the carbon with more hydrogen, so Cl will be here, and then our nucleophile is CH3OH, so I'm just gonna remove this H and I will add OCH3 to this carbon here. One more example. This reaction is an anti-addition reaction. That's why in case if you have a cyclic compound and you were asked to show the stereochemistry, make sure to draw the products in an anti geometry. So for example here, this carbon has one hydrogen, this carbon has zero hydrogen, so my Cl should be added to this point here. So I'm gonna add Cl, let's say it's wedged, and then the OH group should be dashed. Of course, this is one of the products, so you can draw the other one, and in fact you get both. So plus you may get the one which has a dashed Cl and a wedged OH. So both are possible products for this compound. So make sure that your added groups, which are Cl and OH, make sure that they are anti to each other. This is the last example. Here it doesn't really matter, because this carbon has one hydrogen, this carbon has only one hydrogen, so it doesn't really matter where you add your Br. This is going to be my Br, and this is going to be my O-ethyl group, ethoxy group. And of course you can also add the other product, which is the dashed Br with the wedged O-ethyl. So it's a simple reaction. As we will see in the mechanism, there is no carbocation. That's why there is no need to look for rearrangement. You just have to apply the rule by adding again X to the carbon with more hydrogens, and OH or OR to the carbon with less hydrogens. Let's take a look at the mechanism. The mechanism is a combination of the mechanism of halogenation and the mechanism of hydration. So the first step is like the halogenation mechanism, where the double bond, so the pi bond attacks one of the halogens, and this kicks this X halogen out, and then at the same time the lone pair of this halogen just attacks back this carbon. These three arrows will lead to the formation of this bridged intermediate. Now usually in the halogenation mechanism, the next step will be an attack by X minus at this carbon or at this carbon. Doesn't really matter in the halogenation reaction. Instead of that, in this reaction, instead of having X minus attacking this carbon H2O or the nucleophile that is available in the reaction, will attack the carbon with less hydrogens, and this is going to open up this bond. That's why we end up with OH being added to the carbon with less hydrogens, and X will be at the carbon with more hydrogens. Finally, the last step is just removing this extra hydrogen by another H2O, or you can just say minus H plus, and this is enough to complete the reaction. Let's complete this reaction and try to write the reaction mechanism. So first, complete this reaction. Again, in this reaction, it doesn't really matter where you add your ClHO, because this carbon has one hydrogen, this carbon also has one hydrogen, so both are almost the same, equivalent. That's why I'm just gonna put my Cl here and my OH here for now. Let's just focus on the mechanism. So the first step is the pi bond will attack Cl2, so this attacks here, and this breaks the chlorine-chlorine bond. At the same time, to avoid forming a carbocation, the Cl, the lone pair, one of the lone pairs of the Cl just attacks back this carbon here, and because of this, we will get this bridged intermediate which has Cl bonded to those two carbons with a positive charge plus Cl minus. The next step will be our nucleophile is H2O, so H2O can attack either this carbon here or this carbon here because both are equivalent. That's why my H2O will attack this carbon here, and this bond opens up. Once we're done, then we have Cl this carbon here, and then we have OH 2 plus. Again, you can just put minus H plus to get rid of the extra hydrogen. Now why is the reaction anti and it's not like syn? Simply this is an SN2 type of a nucleophilic substitution. That's why it prefers to attack from the back side. So if your X is from the top side of the molecule, let's say this is wedge, then the H2O, when it attacks from the other side. So this is a typical inversion which is usually associated with SN2 reaction. That's why the reaction proceeds with anti stereochemistry compared to the other ones, which may be either anti-syn or none. So this is the halohydrin formation reaction.